Okay, YouTube, in this video we're going to work through a strategy for graphing polynomial functions in general, but this strategy is going to include a lot of good behaviors or best practices when it comes to actually sketching what these things look like. Of course, we know that we're going to be graphing a continuous smooth curve that's bendy and has certain end behavior, but what details can we figure out along the way? So let's go ahead and look at this five-step process here, and then we'll basically put it into practice using a couple of functions that I've got laid out here. So it says graphing this polynomial function, you'll notice that it's this general polynomial function in standard form. We say use the leading coefficient test, or in other words, look at the leading coefficient and the degree in order to determine the end behavior of the graph. So we're going to look for end behavior first and list that all the time. And then, the next thing we always look for with polynomials are the x-intercepts, or in other words, look for the zeros of the function. So what this says here is basically set y equal to 0 and then solve for the x-intercepts. But this also states that if there is an x-intercept at r, so we'd say x minus r was our factor here. And it says x minus r is being taken to the kth power. It's kind of hard to see here. In other words, we get the same answer k times. That is, it has a multiplicity of k, or it happens that many times. Then we say if we have even multiplicity, the graph is going to touch the x-axis but then turn around, not cross that point there. And if we have an odd multiplicity, it's going to cross at that value. So lastly here we say if k is greater than 1, then the graph flattens out near that point r comma 0. So we'll look at that when we graph things here. Also find the y-intercept. So to find the x-intercepts, we plug in 0 for y. Well, this says plug in 0 for x to find the y-intercept. And then number 4 here, this is just kind of a bonus step. It says, but check to see if this is an even function or an odd function to maybe see if it has any symmetry. And then last but not least, use the fact that the maximum number of turning points of the graph is n minus 1, where n is the degree of the polynomial function. That is, whatever the degree is, the maximum number of turning points is always going to be 1 less than that to help you sketch this. So here's what we have. We have this function here, f of x equals x cubed minus 3x squared, and we want to go make a sketch of this. So the first thing we're going to do is talk about end behavior. So now, one thing I notice is that the leading coefficient, I suppose I'll write it closer to here, we say leading coefficient is equal to 1, it's positive leading coefficient, and then the degree of this function here is third degree. And so that's an odd degree. And so in terms of end behavior, we'll sketch this in here, but we say positive leading coefficient means the right side rises. And then because this is odd, it falls on the left. So using this little key right here, we say down up. Down up is our behavior. And actually I'm gonna write this since I have my graph over here as well. I'm gonna say down on the left, up on the right. It's not gonna go through those, but this is kind of our guide here. And because it's down up, this says as x goes to positive infinity and as x goes to negative infinity. In other words, as x goes to the right, if we're going to positive infinity with our x values, what are our y values doing? I notice that they are rising. So we're going to say that these go to positive infinity, whereas on the left side of the graph, that's what this says here. As x goes to negative infinity, it means it goes to the left, whereas the top one is the right. And we say that it looks like we're going to negative infinity with our y values there. So zeros, in order to find the zeros, what we're going to do is we're going to just set the y value equal to 0 here, and we're going to solve this most likely by factoring, which is indeed what we're going to use here. I notice that the GCF is x squared, and that's times x minus 3. And I just want to make a note here. Sorry to beat a dead horse, but we say that's really x times x minus 3. And the reason why I note that is because when we set our factors equal to 0 here, we get x equals 0, and x minus 3 equals 0, which adding 3 to both sides here, we get x equals 3. So these are the 3 zeros here we have. And we could write them into a table. As a matter of fact, though, what I want to do is just go put them on my grid here, my graphing grid. So we say 3 and 0, I know that our graph touches the x-axis here and here. Now the y-intercept, we're going to plug in 0 for x, and in this case, that's f of 0 here. We're going to get this, we're going to get 0 cubed minus 3 times 0 squared, which is just 0, which is already on our graph here, but we wanted to plug that in anyways. So now to check for symmetry, we're just going to plug in our negative x here and see, do we get the same thing we started with, or do we get the exact opposite thing we started with, or do we get neither of those things? So because I'm cubing this here, this will become a negative x cubed. And because I'm squaring this negative x squared here, it becomes a positive x squared, but we're taking it times a negative 3, so it becomes negative 3x squared. Now this is not the exact same thing as what we started with. Not the same, but it's also not exactly the opposite. So there's no symmetry, which is not the end of the world. Honestly, if you have symmetry, that's just like a bonus, okay? So now the maximum number of turning points, because our degree is 3, we say a max of 2 turning points. And so now putting all of this together, essentially, we have a lot of facts about our graph. We know it goes through here and here. We know it goes falls on the left and rises on the right. It's going to have to come up and kind of like turn and go up through again. But we also know that this 0 here has a multiplicity of 2, so our graph is not going to cross at that 0. So in order to get to the rest of the graph here, I'm going to make a sideways t-chart, even though I'm reluctant to do so. It just kills me. I don't like to do it. What my suggestion is this. We're always going to pick x values to the left of and to the right of every 0 here, because our graph is interesting around its zeros, but it's not interesting around further out from there. So noticing that a 0 at 0 here would say that -1 and +1 are on either side, we're just going to go plug those in, -1, +1. And then also that our 3 here is a 0, we'd say we'll plug in 2, and how about we plug in 4. So plugging these in, we're just looking for more points on our graph. And because we have the function here, we're just going to go ahead and do these straight up. We'd say f of -1. We say f of -1 would be -1 cubed minus 3 times -1 squared. So here I'd get a -1 minus 3 times +1, which is -1 minus 3 is -4. So I'm going to put that on my table here, and we're also going to put that on the graph. Left 1, down 4. So I know that point's on my graph. And we say 1. Plugging in 1. The nice thing about plugging in 1 is that you always just end up with the coefficients of whatever you're plugging it in for. That is to say, here, when you, oops, that's not a negative, that's a 1. I'm just going to get this 1 here and this 3 here, essentially. So I'm going to get 1 minus 3, and so I'm going to get -2. And so -2, we'll put that here, and we say at 1 comma, -2 is on the graph right there. So now plugging in 2, we say f of 2. I'm just running out of room here. Of course, you could certainly do this on a calculator or on a different piece of paper or on the same piece of paper if you organize work better than I do. We say, well, then we get 8 minus 3 times 4 is 12 is -4. So -4 here, so right 2, and we're going to go down 1, 2, 3, 4 here. And then finally plugging in 4, I'm going to kind of try to squeeze this in over here. We say f of 4 would give us this 4 cubed minus 3 times 4 squared. And so in this instance, we get 4 cubed is 64. And then 4 squared is 16 here. So we would get 3 times 16, which is, I believe, 48. What we get left over with then is, let's see here. Let's see, 14, 16, 16. And that's a positive 16. So we put that on the table. And so here's what I love about this graph. Now, the last part of this is essentially knowing what we know about this. We know that it can have at most two turning points, and it doesn't cross at this 0 right here. We're going to have to connect the dots with our end behavior here, kind of looking like this, and that's not the best graph way to start that graph there, but we say it turns around here, doesn't cross, comes back down. So it turns, and then here's our second turning point where it comes back up through. I'm going to lift my pencil up here, but I know that it increases without bound on the right. And just because of the fact that we get 4 comma 16, which doesn't even fit here, I can't say do something like that, because I know that it's not at this height when x equals 4. So let me get all that garbage out of the way here. We would say that my graph must look something like this. And it's always good to go check your graph on a calculator to see how accurately you did your work there. So let's look at one more example here. We're just going to put this together a little bit more quickly this time, except for I wanted to look at an example where we have an already factored function. So it says use this 5-step strategy to graph this right here. Well, I'll tell you what, the first thing we did last time, we talked about end behavior. And what I can tell you is because this is already in a completely factored form, what you're going to see here is that really we have 2 times x plus 2 times x plus 2. If we list these factors out here, x minus 3, what I want you to see is that you have a first degree thing times a first degree thing times a first degree thing, which means you're actually overall going to have a third degree thing. And we could FOIL this out, but it's really not worth our time to do so because it's actually a lot more valuable if we leave it factored like this. It saved us the time of having to factor it. So what I know is this. We know that we have at least a third degree just by listing these out and counting up all the degrees of our individual factors. And the leading coefficient, this will do a satisfactory job of telling us that the leading coefficient is 2. So that's a positive thing. And we have an odd degree. So what we know is this, the end behavior, I'll write my little key here, and I won't put a comma there. But we say positive leading coefficient means rises on the right, and odd degree here means it's opposite on the left. So we'll put this on our graph. It must be down and up, or falling, rising orientation here. And so we're going to write that up here also. As our x values get very big, our y values are going to positive infinity. And as our x values go to the left here, our y values are going to negative infinity. We can see that right there. So zeros, let's set this equal to 0 here. Set the y values equal to 0 and solve for the x values that cause this to be true. And again, the nice thing about this is that it's already factored. So dividing everything here to get this 2 out of the way. We don't need the 2. what we get left with is 0 equals x plus 2, and I'm going to list this out here, times x plus 2 times x minus 3. And so if we set this and this and this all equal to 0, what we're going to find out is that x plus 2 equaling 0 gives us x equals negative 2. And I'm just going to put a box around that. And then here we're going to get x equals negative 2 again. And then here we're going to get x equals positive 3. So I'm going to put dots on the x-axis at negative 2 and positive 3, right there and right there. But what I know is this, because at negative 2 we have a multiplicity of 2, that we're not going to cross the x-axis right there. So our y-intercept, to plug in 0 for x, that's really kind of a simple thing to do also. We already have this function in a manageable format here. So we get this here, we would say this would be 2 times 2 squared times negative 3. And then so we would get 2 times 2 times 2 is 8 times negative 3 is negative 24. Negative 24 here. And let me just check my math here, just make sure I did this right. We have 2 times 2 times 2 times a negative 3. That certainly is a negative 24. So we're going to hold on to that, because that's one thing that doesn't even fit on my graph here, which I kind of love about this problem. And we say symmetry. Okay, so symmetry. If we plug in a negative x, let's see what happens here. I would get f of negative x would be 2 times negative x plus 2 squared times negative x minus 3, which is not the same thing we started with. And as a matter of fact, it's not exactly the opposite thing we started with, so this has no symmetry. Okay, and then turning points, because it's third degree, we say it's 1 less than that, so we say at most 2. So again, we can get an idea that our graph probably comes up, touches here, turns back around, and then comes back up through here. What I love about this problem, other than the fact that I have more room to write a vertical t-chart in here, is the fact that our graph is going to leave the coordinate grid here as we have it drawn out if we're going by ones. So in terms of what x values to use, I would say since negative 2 is a 0, we do negative 3 and negative 1. And also because positive 3 is a 0, we'll do positive 2 and positive 4. So let's take a look at this. Also, I'm going to include 0 here because 0, negative 24 is also this point that we put right there. So we'll plug in a few values here. And so we get f of, and we'll start with negative 3, f of negative 3. We're going to get this plus 2. I'm going to work a little bit out of the way here so that I can unwrite some things. But negative 3, if we put in a negative 3 here and a negative 3 here, I'm going to get negative 1 squared, which is 1. And over here I'm going to get negative 6. So we get 1 times a negative 6 is negative 6. So I'm going to fill that in up here, negative 6. So now if we plug in a negative 1 next, I'm going to say negative 1, negative 1. I'm going to get a positive 1 squared, which is 1. And over here I'm going to get a negative 4. So 1 times negative 4 is a negative 4. So we get a negative 4 here. When we plug in a positive 2, so we say 2 and 2, we get 4 squared, which is 16. 16 times a negative 1 is a negative 16. So I'll put that here, negative 16. And then we plug in a 4. So 4, 4, 4. I'm going to get 6 squared, which is 36. 36 times a positive 1, which is a 36. So, 16, 36. So here's the fun part about this. Some of these we're going to be able to graph and some of these we're not. And so I'm not going to change my scale here, but I want to not do that just to show you the significance of the table. We say going left 3, we're going to go down 1, 2, 3, 4, 5, 6 would be about right here. We'd say negative 1 down 4, so that'd be right here. And then we'd say 2 comma negative 16. Now I can't graph down that far, but I know it's way low, and I also know at 4 comma 36, that's way up here. So what this is going to look like is a graph that comes up through here. We know because this has an even multiplicity, it's going to touch and turn around. And then I've got a graph that's going to do this. And in this particular case, because I'm not changing my scale, it leaves and hits down at 0, negative 24, and then doesn't come back, 2. Even 2, it's at negative 16, so it doesn't come back until we get to here. And just to let you know, I'm going to finish drawing this in here as best I can. It actually, remember, leaves and goes down and comes back up in between here and here. So this would be our polynomial function as we know it. Cheers.